slightly better pen. Yeah.
Well, I just opened this pen, so hopefully.
Okay. Okay. So, welcome everybody to this last week. We have master classes this time. By the first master is Apoorva Khare. I mean, all Indians know him as the recent SSB award winner. But yeah, as part of our commitment, he has agreed to give this masterclass on BGG category O, and he will also talk about the connection with quivers in this week. So, Apurva, over to you.
Okay, thank you. Thank you, Amit, for the warm introduction. Thanks everyone for being here. Yeah, so I will let me start with the sort of a little recap of what happened last week. So, yeah, so what you saw was I talked to Ravinder, who just finished the last week, and so what we ended up with was okay, maybe I should start with some notation just to remind everyone the weekend is over. So, yes, so the one thing I did not ask him is if everything was over complex numbers. So can anyone tell me that that was what was decided? Or we do
Yes, yes, over
Yeah.
C.
Algebraic.
Yeah, you can also do algebraically closed field of characteristic 0, but let's do over C. So everything is over C. So G is finite dimensional semi-simple D algebra. Over C, it contains, we will fix a Cartan algebra. And corresponding to the Cartan algebra, you have a set of roots. So this is all visible, right? Just to check again. Somebody tell me. Okay. So this is the root system, which contains a base of simple roots. And we will denote this base by in two ways. So I'll just sometimes one will say just alpha, alpha and delta, or one will say alpha I in I. Then I is this indexing set that denotes either the simple roots or the nodes of the ring in diagram. Right? So all this is the standard, this same notation as last time. Now corresponding to this, so G is of course, okay, maybe let me first do the roots part and then go back to G. Right, so then for every alpha root, we have this simple reflection S alpha from H star to H star. Just in case we lose these, I have another black pen. Okay, as I said, this is a simple reflection. In fact, let me even say better. This is an orthogonal map on H star. There is this inner product, and this is preserving that inner product. And then these S alphas generate the while group. Right, so that's the while group. It's a finite reflection group. Okay, what else? Great. And of course, again, you must have seen the simple base. Please let me quickly draw one of these simple bases in type, let's say G2. Right, and then there's this is alpha, this is beta, and then every, so roughly speaking, you have these positive roots. These are the 5 plus. Every root in here is a positive combination of alpha and beta. This is beta, this is alpha, this is beta plus alpha, this is beta plus 2 alpha, this is beta plus 3 alpha, and this, the top vector is the highest, unique highest root, which is to be denoted by theta, which is 2 beta plus 3 alpha. So this part above the line is 5 plus. Maybe I should draw the line. The things above the blue line are 5 plus, and everything below is negative of the roots above. So they are written in terms of negative integer combinations of the simple roots. And this is the unique highest. This is time G2. Okay, so just to recap. Okay, what else to recap? I have 2 live audience members here as well, so they can ask me questions. Sometimes they will. Okay, great. Let's see. One thing I do need, which we will be needing later for category O, is the height function. So the height function takes, I don't know, H star to C. Really, I just actually don't care about the full H star. I just care about the root lattice or the weight lattice, but anyway, you can define it, that's defined. Right? So the point is, delta is a basis of H star. So therefore, any element of H star can be written as summation Ci alpha I in I. Right? So the height of this function is simply summation Ci. So that's the definition of the height function. We will need the height, as I said, mostly for integer combinations of roots, but yeah. Okay, great. So that is all various recaps. So now that is on the root systems and the root side. One more thing. Fine. Let us, since we're talking about roots, let's also talk of weights. So weights, yeah. So weights are simply elements of H star, and the integral weights are those lambdas such that if you take this angle bracket, lambda alpha over alpha, so there's no over, then this is an integer. So either you can take all alpha in the root system or all alpha in, let's just take the root system. But anyway, alpha and delta. Okay, these are the weights, integral weights, and the dominant weights are simply those lambda and H star.
Yeah, hello, am I audible?
Yes,
Yeah.
go ahead.
Yeah, you have to type alpha check, no? You mean lambda alpha check?
I'm not evaluating, so lambda alpha.
Oh, okay, sorry. Okay,
So
fine.
this is also equal to, as you said, it's inner product of lambda and alpha check, but sorry, I should really make the angle bracket more angular.
So lambda alpha.
Sorry, what?
Lambda
Sorry,
alpha.
inner product. So that is not inner product, that's evaluation. Right. Okay, great. So dominant weights are simply those such that lambda, and let me just say alpha I bigger equals 0 for all I and I. Okay, so these are dominant weights, integral weights, and the intersection of these is called, let me call this A, let me call this B, and A intersect B is the dominant integral weights, which we defined. So these are actually the ones that characterize that, characterize or index the highest weight finite dimensional, index the finite dimensional irreducible modules. Okay, so then the final thing I need to probably say is that this contains these fundamental weights. So these I will denote as, this is not omega or w, this is apparently var pi, which if you write in latex, this is actually a variant of pi. So var pi I, basically this is given by var pi I, alpha j is delta I. For all I. So in particular, this is in some sense like a dual basis, right? So what I'm really saying is the following. So say, suppose say, let's say G has a 3 or G has rank 2. For example, SL3 or type G2 or B2 or whatever. And I know that lambda in P plus, or that's lambda in H star. It's really in P plus. It's defined. Has lambda of, so maybe I should have pointed out here. So corresponding to these simple roots, one writes down these Chevrolet generators. Has Ravinder used EI, FI or XI by I? No, the audience should tell me.
EAFI.
Yeah, I'm very happy because that's what I will use. These and then the HI, which is the bracket of this guys. And each of these for all I and I forms a SL2 triple, right? These span a three-dimensional. These are the basis of a three-dimensional least algebra of G, which is isomorphic to SL2. Okay. So if you look at, suppose lambda of HI, let's say H1 is 3 and lambda of H2 is 5. What can you write down lambda itself in terms of the fundamental units? So maybe that's the first question I should ask people. Do you ever see this? So the answer is the answer. So consider this. Call this lambda prime. Okay. So how much is this at h1? So okay. So maybe the correct answer is this equal to omega I of hg? Right. This is because this is omega I of hj. Therefore, this is exactly going to be 3. And if you were into h2, it's going to be 5. And because G has rank 2, so these spans, you determine this linear functional on all of H. So on all of H. Sorry. So therefore this is exactly. So basically, all you need to do. So that's the point of this is that if you read off, if you have any say dominant integral weight, that means it takes non-negative integer values. This could be zeros. Non-negative integer values, and Z at every single HI. Or alpha, yeah, at every single exam, right? But then that's the point is, those are precisely the coefficients of the fundamental weights when you write lambda. And now the point is, I could have replaced p plus by something like h star, and I could have said this is 3 pi and 5 e. And I could take irrational numbers. In fact, 3 pi I. Then I can take 3 pi I here and 5 e. Because you get exactly the same scale. So fundamental weights are basically a dual basis. Okay, so now let me get back to the algebra side. So we have, so since you just ended by seeing Verma modules, this is good. That's exactly where we will start. Where is my eraser? Oh. Okay, so did Ravinder also? So okay, fine. Let's start with G modules. So first of all, the finite dimensional ones. So by Wild's theorem, this is the direct sum of the irreducible finite dimensional ones. Right? So it suffices to understand each irreducible one, and then you understand the action of G on any finite dimensional module. So how do the irreducible ones look like? So G, so finite dimensional G irreducible representations over complex numbers. Again, everything you see are in one correspondence with this dominant integral weights. Here is p plus here, right? And for any lambda here, you get. I hope I don't know. He called them V lambda, I guess. That's what Ravinder told me. But we will call them L lambda in this class because we are now going to talk about this paper of Bernstein, Gelfand, and Gelfand, a category of G modules. And in this paper, the simple modules are L. And the Verma modules are M. So M is still fine already. And we will call the simple modules L lambda. And this is finite dimensional. You can define this to be, so okay. This is done already. Yes, PBW theorem and UG is done.
Yes, sir. Yes.
Good. Oh, so then this is UG. And then out of, so basically UG is the same as, if you think about these as left modules, UG is the same as UG times 1 because it's a unital algebra. You can quotient by the ideal where you apply, where you kill something. So you kill EI times 1 for all I. And then so you can say UG times this summation plus UG times summation I and I. HI minus lambda of HI. Sorry, again, I should maybe put the usually inside the summation. Plus, again, now I UG times Fi. Now lambda of HI is a non-negative integer. That's what this means. Right, so plus 1. Now this is a strictly positive integer, and I can again 1 So yeah, you quotient. So now obviously this is left submodule of UG, and you quotient by this. This turns out to be finite difference. Okay. And now notice that the only place where we use the fact that the lambda which is an integer, positive and non-negative integer, is here, because we are raising some vector in an algebra to some power. We have to raise it to integer power. So what if we forget this condition? What happens if we do that? So that's where that was what was called the Verma module. Yeah. And that gave us, so yeah, so maybe I should say this, in a lambda, the image of one, let's call this, let's say v lambda, uh, is a maximal vector. Was maximal vector defined? I'll mention it again, but was it defined anywhere? What this means is that if you apply, yeah, actually maybe I should say the following first, right? Let me just remind you that the EIs and so on are there, but if you look at notation, if you look at the direct sum of all the positive root vectors, root spaces, this is the Lie subalgebra. Lie subalgebra of G generated by the EIs. And this is what we call N plus. In, for example, SLN, this is the set of upper triangular, strictly upper triangular matrices. Similarly, and alpha belongs to phi plus, G minus alpha is the least subalgebra generated by the FIs, which is the definition of N minus. Okay. So here now I can say that instead of saying the EIs kill all of EIs all kill this vector, I can say that the whole of N plus kills it. And H, any vector H acts on E by a scalar. So V lambda is a vector that's simultaneously an eigenvector for the entire Cartan surround. So this is an example of maximal. And so now we will look at this maximal vectors in any G module by only finite dimensional ones. One quick point to note here is that if you have this thing, then a G is N minus direct sum H, direct sum N plus, and then because of that, then by the BBW theorem, you can look at the multiplication map from U N minus tensor U H tensor U N plus to UG. This is the vector space isomorphism. So this isomorphism is what we will use. So again, I am recapping things that we have seen before. So now, fine. So now let's get to maximal vectors. And actually, one thing I will use is this isomorphism when we talk about elements of the center. Yeah. So first of all, now this means that you have so one can define maximal vector of weight, let's call it a mu in H star in a G module. And it simply means these two conditions are satisfied. So a maximal vector of weight mu in any G module, so any weight mu in any G module is a vector, a maximal vector. is M belonging to M such that, sorry, let's say it's a non-zero vector M belonging to M such that N plus M equal to 0 and H M equal to mu of H. So this is a Maxwell vector. And the nice thing is that every such vector generates a submodule. So each such, I mean, every vector generates a submodule. There's nothing special in that. But the submodule is particularly nice because now we can apply this PBW as well. UG times that, right? So by the definition of how modules look like, UG acting on this is the same as some multiplication. So you can multiply monomials here, then here, and then on it. Times UH times UN plus times N. Now, what is UN plus times N? I hope you guys have seen this before. If M is maximal, then what is UN plus times N? Then N plus M. So
it's 0. It vanishes. Not 0. It's scalar multiple of M.
Scalar times N, because UN plus also has the 0th degree component, which is the scalars. So it's just every positive degree component kills N. This is just scalar. Maybe not direct sum, but actually direct sum is correct because the augmentation ideal is still 9. Okay, so fine. And now what is UH times a scalar multiple of M? Well, anything in H acts by a scalar. So if I multiply by monomial in H, it will act by products of these scalars. So you still get UN minus. And then now, so it's UH times M. But now UH times M is again the same as C times M because everything is a scalar times M and the one vector sits inside here. So all scalars sit. Okay. So therefore, this is equal to, so it's really UN minus N. So UG times, so whenever M is a maximal vector and you're applying the entire universal enveloping algebra to it, it's enough to write the elements of that algebra in this kind of a form, in this order of words. By the PBW theorem, you can choose any order of words. Choose this order, some basis of N plus, some basis of H, some basis of N. And then you can ignore everything that is a non-trivial word coming from. Fine. Great. Fine. So these are what maximal vectors are, and this is how the entire UG acts on any maximal vector if you ignore the first two parts. Okay. So now let's see. So maybe now is the correct. Maybe this is a decent time to do something new. So let's write down some. Let's talk about the center of UG. So you have any unital associative algebra. It has a center. Have you seen this? Have you seen any results on this already in the past week or something? No, I will take that as a no. So, so there's a theorem that there's a famous theorem by Harishchandra. Actually, there are some. It's a combined Harishchandra and Chevalier's theorem. Maybe I'll just say this is just saying that the center. So that we call this Z of UG, and so this is just the set of all x, capital X in UG. X y equals yx for all y. I mean, I'm sure you all know the definition of the center. Write it down for posterity. So the point is the center of UG is isomorphic to the symmetric algebra of H, which okay. So W itself acts on H star. The line group acts on H star. We have simple reflection. So transferring using sort of the killing form, W acts on H, and if W acts on any vector space, it acts on higher tensor powers and symmetric powers. So vector space, if the action is nice enough. In this case, it is. So the only thing probably I should say is that this action is not the usual action, but a twisted action. Yeah, that's so okay. So yeah, so this is a twisted action, and this is the actual isomorphism. Anyway, the point is whenever
Sorry.
finite.
Sorry, what did you say? This is not shifted action, right?
But it's not the twisted action. When you evaluate central scale.
Sorry, actually, your voice is a bit unclear to me. I'm sorry.
It was not the twisted.
After twisting it with row, you need a double invariance.
The invariance of what?
Of the polynomials. After you twist them
by
row, then you have double. Otherwise, it is invariance on the dot action, but then you add row and subtract row to the Alexander homomorphism.
In the homomorphism.
Sure.
Okay, fine. Okay, there is a finite group acting on this. The invariants are this. Yeah, okay. Good. Thanks. We will have later doing this. Now, this by Chevalier's theorem. So, okay, first of all, what is C-match? C-match you can think of as the polynomial algebra in H star. So, C-match is a polynomial algebra in I many generators. Now, there's a theorem by Chevalier which says that when you have a finite group acting on a polynomial ring or polynomial algebra in so many generators, the invariance of that over, say, complex numbers, the invariance of that is also a polynomial algebra in some number of generators, in the same number of generators. So, indeed, what the center of this thing is going to be a polynomial algebra. So, all I'm trying to say, therefore, is that the center is isomorphic to the polynomial. That these guys are the elements of UG. One of these elements is, one of these central elements is called the Casimir element, and that's in degree 2. So, no, for this. Anyway. Good.
Alexander homomorphism is into W dot orbits.
Okay, the twist, that one is that one. Okay, fine. Okay. The central character is there. So that is where we are going next, which is where the dot action gets used. I will leave that. Jumping the gun. So now what I want to do is the following. Fine. You have a central element. You have a module which is, let's say, so now ask a question. Say M is the highest weight. I'll denote HW as highest weight for vector of weight mu. Sorry, not highest. I meant maximal vector. Sorry. I keep using them interchangeably. Arbitrary, I don't care. In some G module. I don't care if the module is finite dimensional or not. Okay. And Z is a central element of U. How does this central element act on it? In fact, on the entire module. So that's the first question we are going to discuss. Now the point is the following. Let's first look at how Z acts on N. So it's central element, it sort of commutes with UG. So, now as we said, you can write down any element of UG in this PBW form. So before we do this, before the previous questions, how does so can one give some more information? Info about Z in PVW basis. Okay, so the point is the following. So let's just look at SL2. Okay, so example SL2. So you have exactly three elements F, H, and E. So every element of UG, let's say Z in ZUG, but in fact any element of UG is of the form summation. Let's see, Fi. Let's say I don't know Cijk. Some space for the scalars. Cijk Fihjek. This is how you would write it down in the PPW basis. Because all of these spaces are one-dimensional, F, H, and E. So the universal and the algebras are simply polynomial rings in one generator. So everything is of this form. Now, because it is central, let's look at what happens when you take H bracket Z to be 0. Because it's in the center, so HZ minus ZH. Maybe I should say. So maybe I write it this way. But this is the same as H bracket Z. So the whole point is in the universal and null algebra, that is the associative algebra in which the Lie bracket is exactly the commutator. So this is the commutator, so this is the Lie bracket. So summation Cijk, Fi, H. Suppose, of course, I'm assuming that all of these are non-zero over some subset of indices. I think. So Fihj, Ek. Now do the calculation, which I will not do, and you will check that this is summation Cijk, and then there is what? It is twice k minus twice I, Fi, Fj. Okay, but I need this to be 0. And of course, the point is these monomials are linearly independent by the PVW theorem, and the coefficients are non-zero. So the only indices over which this can sum up and still give 0 on this side is whenever this term must be 0. So k has to be equal to I. So every time you have a power of a lowering operator, you must have the same power of the raising operator if your element is central in all PVW monomials. So I hope that is clear from this calculation. The same thing happens now for any semi-simple algebra. So let me just say that. In general, every Z in Z in the center is of the form is this handwriting too small or is visible? Let me know if it's too small. Okay. It's summation. Let's say I'll give this a name. Let's say Fi, meaning you order your PVW basis. You take some basis of n minus in some order, and it's a multi-index, and then H, J, and then E, and I put the same I. Oh God, not I. Fine, thank you. I is used for simple roots. So F, K, J. So K is a multi. So F, K is F. So maybe I'll call this. There we order the positive roots as say beta 1, beta n, and then you write Fk is the word F beta 1 to the K1, F beta n to the Kn. Do I want the reverse order or the same order? Probably doesn't matter. Just for fun. You can choose any order, I guess, but I'm choosing this to be Maybe I'll include the reverse. E beta into the K and E beta. And H is some polynomial. Sorry, not J. Yeah, this I is correct. Because I is these are commuting, so it doesn't matter what. I'll just choose some order. Huh? Okay. Then multi-index you fix some order J1, J2 in some order. Okay. So every central element is of this form, but this K is the same as this K. So for beta n, there's a K in here. This beta n has to be K because the simple roots are well. Oh God, no. Yeah. This is not true. Yeah. Sorry. Let me call these K prime. Sorry. Oh, this was correct. There. What we need to say is the following. So the point is, there can be repeated. So I could have something. I'll explain to you after this. Let me write down the condition. Summation K I beta I equals summation K prime beta. Oh God, let's call these as G's. And let me explain why. Why I don't need all of them to be exactly equal. What I need is that the H action should be 0. So when H acts by getting commutator, for every H in the Cartans of algebra, I should get 0 because Hz minus Zh is 0. Now, what do you get when you multiply Z? The reason being, if you look at H bracket F power K, I don't somehow distinguish between all the K. What I get is it is summation, maybe I'll do E power K prime. So K prime J, beta J, evaluated at H. Okay. This is true for all H and H. And similarly for F power K. So I must get the whole thing to be 0. So I must get this summation plus this corresponding Kj minus beta J H to be 0. And this should be true for all H in H. Therefore, the functional itself, this minus this, should be 0. So that is how you would write down any element of the this form. So now let's get back to this original question. How does Z, a central element, act on M? M is a maximal vector. So the moment I have anything here, any word here, where even one of the powers is positive, even if it is just one monomial and its power is 1, that's the simplest. Or anything, any word where at least one of the K prime is positive, then it has to kill M. Because everything with a positive root vector kills M. So therefore, when you write this down, most of these monomials will correspond to. So what does it mean for this power to be, at least one power to be positive? Maybe I should write that down. Now, summation, what was this? Summation K prime J beta J. So K prime is not equal to 0, 0, 0. Meaning it's of course bigger than but not equal to. Is if and only if this K prime J beta J belongs to right? So suppose I've given non-negative integers K prime J such that they are not all 0. That is if and only if this summation is a non-zero non-negative integer combination. Because there is at least one positive root and therefore it has at least one simple component. But the moment that happens, it basically means that, how do you form such a generator? You form it out of these simple. So it means that e power k prime acting on this highest maximal vector. Yeah. Which means that the entire word is. So I'll just skip a line and just say. So this part of the center, of course, in general, actually no, if anything kills zero, then the full word obviously kills zero. Right. So therefore, now what remains? The question therefore is we wrote down a central element, a general central element in this form, and the summation of these guys. And the condition was that k prime is zero, k prime is non-zero means this thing and then this happens. But now here is the other point. If k prime is non-zero, then it also means that this summation is non-zero, but then this summation is non-zero because they are equal. This summation is non-zero if and only if k is non-zero. So we are now therefore killing off every word or summand that occurs in Z when you write it in the PBW form, and then you should call it PBW. We are killing off everything here where the k prime and the k are non-zero, non-zero, yeah. So Z acts on M precisely over as a, I should have called this some scalar. See A, J. So I will call it here C0, J, 0. H power J. M. So every central element just acts by the purely H part of its word decomposition, PBW decomposition, when you choose the ordering as n minus, then H, and n plus. And so, for example, in SL2, I could show you something like that. That if I have something, so again, for example, in SL2, I'm not saying the following element is central, but let's say F cube, let's say P3 of H, E cube, plus, so the scalar part of it would go inside this P3 of H. It's a polynomial in H, plus F fifth, P5 of H, P fifth, acting on M, of M is of highest weight mu. I also didn't note down the mu part. So let me note this down afterwards. So first of all, this is equal, sorry, plus P0 of H. There is no actual F to the 0, there's F0 and E power 0. This is just literally the same as P0 of H. I was assuming maximum vector to be of weight mu. I erased it, but I think it's a maximum vector of weight. So, and now therefore, but now when you evaluate anything of a vector of weight mu, you get P0 of, what should I write here? If I act by H on mu, what do I get?
Mu.
I get mu, but I'll just be more precise and say mu of H. Just because in the general case, that's what's going to happen. This is going to be yes, summation C0 G0 times mu of Hg. This is the scalar by which you would act by any center. So there is now. So now let me tell you that there is a map that takes every element in the center, or every element of weight 0, let's say, to just the purely Cartans of algebra. Let me give you the definition. So definition. The Harishchandra projection of that. Projection from Z UG to UH, the Cartans of algebra part, sense, yeah, as I said, sense summation C J K, sorry, KJ K prime. A j k prime, f to the k, h to the j, e to the k prime, to just the 0, 0. C0, J0, H power J. Let's give this map a name. Let's use Humphreys.
Yeah.
He calls it PR. Okay. Following Humphreys, we will call it PR. Or the Algebra Lecture. Okay, great. So now, once we have this, we can now complete. Now we can write down the answer to this question using this map. So let's see. Yeah. So therefore, first answer part A, I guess. Z. This is in Z mu d times m. This is maximum of 8 mu equals mu applied to. So remember what was mu? Mu was an element of H star. And mu belongs to H star. Which means mu sends H to C. But then I can say that this extends. This is the universal property of tensor symmetric algebra. Yes. Given any linear map from a vector space to C, it extends to a polynomial map from a symmetric algebra to C. Because you just take mu. So, for example, if I had something like h1 times h2 cube, then this would map, for example, to mu of h1 times mu of h2. That kind of thing. Right? So words go to polynomials in those words, and you extend by linearity. So now, therefore, mu here is an algebra map, taking elements in PR, right, which is this. Great. Okay, any questions? Please keep asking questions. So this is how a central element acts on the maximum vector. But then I can say this is how it acts on every vector. Right? So for all x in UG, if you look at the central element acting on x times them, and because the center commutes, you again get the same. It's equal to then you get x times the scalar times m. The scalar comes out. And so Z acts on the entire submodule that is generated by M. So now we come to finally, let's remind ourselves of Verma modules. And maximal vectors inside Verma. So now we don't want to say anything else before that. I don't think so. Fine.
Mu times 10 also in the first answer.
Oh, okay. Yes. It's a scalar times m. Yes. It's not a scalar. Yes. Right. So we wrote down the definition or the formula for the simple module, which was finite dimension. It was UG quotiented out by UG times 1, quotient out by the summation UG times the EI and it times 1 plus summation UG times H minus lambda I of H, sorry, HI minus lambda of HI times 1. And then plus something with the FIs. But now, as I said, the only place where we use the fact that lambda was dominant integral was in this third term. So what if we don't actually have lambda dominant integral, and what if we correspondingly don't quotient that? This is called the Verma model. This is what one defines. Humphreys calls it Z of lambda in one book, and then M of lambda in his next book. We will just use M of lambda. Okay, this is the Verma module, highest with lambda for any lambda. Lambda. And so Ravinder did this, the basic properties of this module, right? So now because of this thing, you can check. So check by the PBW theorem. And maybe this was already done in the tutorial last time. So what we said earlier was that if you have any higher state module, then right. So if you look at M, which is maximal in M, then that means that UG times M is just the same as UN minus times M, because other things just either die out or become scalar multiple, right? That means that M lambda. So here the image of one is going to be called that M lambda. The definition is the image of one. So that means, of course, UG is generated by one vector, so that M lambda is for the generator of M lambda. So M lambda is UG times M lambda. And now M lambda is maximal because by definition, EI times the image of one is 0 in the quotient model. EI times 1 is not 0 here, but we are killing off EI times 1. So EI times is 0 in the quotient. So now, because of what we just said here, I can just write this down as plus UN minus. And now here is where the PBW theorem gets used. There are no relations involving N minus over here. When you, so, yeah, of course, erase that. Right? So it is, remember that UG is isomorphic to UN minus, tensor UH, tensor UN plus. Using that and this thing, I'm just calling that the PBW theorem. Maybe you can do that in your M lambda. The map from UN minus to M lambda, sending X to X times the image of 1. This is a valid vector space map. In fact, turns out this is a vector space isomorphism. And it's not just a vector space isomorphism, it's isomorphism of UN minus modules. This is generated by 1 here, this is generated by lambda here. They're both generated by a single vector as UN minus modules, not UG modules. This probably Teja will look at in the tutorial. Basically, you write this down as UN minus tensor US tensor UG. And just like we killed off one term at a time here, you just kill off the terms. I hope that you can check that in the ideal, there is nothing that UN minus intersects. And that's basically because, yeah, if you look at UN minus tensor 1, this intersects this basically 0. So far, again, of course, you will notice that this is supposed to be a master class on category O. I have not talked anything about category O yet. And that's because Varma modules and highest state modules are really the building blocks of category O. So you already saw those, and now we are going to see, and the center is actually very important. So how the center acts. So now let's say, this I think Ravinder also did. So say M, I should be maybe numbering these things. Let me call this number as 5. You label 1 through 4, however you want, previous and continuous. So, so say M in M lambda has what is maximal. Just not use my hands. Okay. What can we say about? Is there a connection? Is there a connection between them? Is there R lambda and mu? How R lambda? Now, for example, for SL2, I think you already saw this. Did you see this already?
Yes, but
Yes.
Yes, it's, you can recall.
And what is Sorry? Ravinder said
Yes,
yes.
yes, but you can recall. Because
But
no
I-
SS from others.
Because if Ravinder is saying yes, then that is not a real yes, let's say. So yeah, let's recall this for the students. Yeah, so what happens then is that you have to do SL2 theory, which I'm not going to do. But basically, you see that the Varma module here, now m lambda, because of what I just wrote here, is isomorphic to un minus, which is just the polynomial value 1. So it's really, so what we are saying is this is really just the same as, I can maybe say, it's the direct sum. Where do I keep my eraser? I forget the rate. Yes. I have too much stuff. So, okay, it is the span or has basis. It is basically this thing, but applied to the highest state. So it has basis m lambda and f m lambda, f square m lambda. And now, if you do SL2 theory, what you will check is that so now, okay, and notice that the weights are, what are the weights? This weights lambda. What is the weight of this FM lambda? Have you calculated? Does anyone remember?
Lambda minus.
Sorry?
Lambda minus 2.
Lambda minus 2. Let me call it lambda minus alpha because your F is the vector of beta. So alpha of H is 2. So the eigenvalue is 2. So lambda is if you think of lambda as a scalar, then yes, it should be lambda minus 2. If you think of lambda as an element of H star, then this becomes lambda minus alpha. It's the same thing for SL2, scalars and elements of H star. In general, we will use this notation. Okay. These are the weights of the. So in particular, these vectors are of course linearly independent because they have distinct eigenvalues, characteristics 0. So they are linearly independent, and these are the. And this is exactly the full basis of this. So if you have any maximal vector of some weight, then it's an eigenvector. It is one of these guys. It is this, or this, or this, up to some scalar function. Which one of these can it be? It turns out it can only be exactly one of these, and in a very special case. So if you use SL2 theory, to compute. So what does it mean to be maximal? It means that it has to be a weight vector, so it's one of these guys, and it has to be killed by the entire positive subalgebra. But in SL2 there is only one such root space, just E. So 0 equals E times, let's say, f to the j m lambda. Okay, this will give you. This implies two things. One is that lambda itself is a non-negative integer. Lambda cannot be like root 2. Lambda which cannot be root 2 or even negative. It has to be 0, 1, 2, 3. And secondly, j equals minus lambda of, sorry, j equals lambda of h plus 1. Both of these conditions follow from just this calculation or from SL2 theory. So this is a very nice, obvious thing to do, very hands-on calculations to do when you have SL2. What do you do when you have any simple algebra? Then you have to use a theorem of Harishchandra, which is again Humphrey's book, to tell us what happens here. So this was just using explicit calculation of the raising operator. That is sort of harder to do there, but what we use is exactly the action of the center. Okay, so now let's write this. So sorry, what?
If we reverse the order of weights, we will say that this will happen only when lambda is correct.
Okay, correct. Maybe the correct answer is this. First you say this. And now the calculation turns out to have this j minus this, or lambda expression minus j times something. And the correct, maybe I should say this. You can check this calculation if you want the full details. times some non-zero scale.
J plus 1.
I don't even care. So if you do the calculation, it belongs to it's a non-zero scalar times this number times that. Okay, and now therefore, first of all, j has to be equal to this, and then as Teja said, thank you. Therefore, this number has to be a number. It has to be a positive.
F power j minus 1 is missing.
So yes, thank you. And now, so okay, I started by assuming j positive, I suppose.
We want to maximum of the property.
Let me start by saying use. So yeah, so for SN2, life is easy because we have explicit formulas to calculate such. This was the first week probably. Right? The problem is what happens when you do a general science algebra. In that case, we have to do this. So now let me maybe write a definition down here. The central character for associated to mu is chi mu from the center of UG to C, sending any central element here to exactly this. This is the central character. Now, this central character is what is going to be used to answer this question. And yeah, I could have done this after introducing category O. As you can see, I don't use anything about category O here. So I want to do this first, then we will get to category O, and then we will actually use. Sorry about that. Okay. That should find out that my phone is able now. Thanks. Okay. Okay. So this is the question we answered. So this was the example was fine. This was part B. Let me call this part C. And now we can answer the question in part B. So how are they, right? So now answer 2. Oh, wait. First, let me put, since we are talking about central character, I'll write down the name. The central character chi mu is an algebra. A priori, mu is a linear functional, which of course extends to an algebra map. The projection was some map that takes a summation, whatever, Fk, Hj, E, A prime to Hj. The projection took this monomial, TBW monomial to this guy. Sorry. To delta k comma 0, delta k prime comma 0, and then Hj. Right. If either of these is non-zero, then you get 0. If both of these are empty strings, meaning the powers are zeros, then you will preserve the monomial. This was the thing, and then you extend by linearity. So this was the projection map. A priori, it's just a vector space map. Mu is an algebra map, but the claim is that the full thing character is an algebra. This stage I will do in the tutorial. And the reason is because the projection is also an algebra map on the center. This could be defined on the entire universal number in algebra, but it's an algebra map on the center and a slightly bigger space. We just care about the center. So chi mu from center, if the domain is the center, then life is fine. Okay. So now, suppose I have a Varma module, let's say, or even any high state module. and I have the maximum vector inside it. So let me go to D now. So more generally, say M equals maximum vector. So okay, let's say M equals highest state module. Okay. No, okay, let me not do this. Let's keep it fine. Now, okay, mu is not equal to that. Now, there is another maximum vector here, which is the highest state vector of weight lambda. Lambda is not equal to mu. Oh, this was called M, but I'll call it M. So now here is a module, Varma module with two different maximum vectors. Take an element of the center. So before that, I should say, so because now M lambda is the same as UN minus times M lambda, as we saw by the PBW theorem. Therefore, there is some monomial or some word, some combination of words. So such that mu equals x times M lambda for some x, which is a PBW combination of basis vectors. So now I can act by the center. So for any central element, what do you have? Let's look at how it acts on M lambda, mu. So first of all, because it acts on mu, we already said that it doesn't matter how whether mu was maximum. Mu was maximum, but not necessarily in the Varma model. This was done before this. Therefore, this is equal to chi mu of Z M. Because that's the definition. This is exactly chi mu of Z, the central gap. But also, if you look at how Z acts on mu, mu was equal to x m lambda, so Z times x m lambda. But Z and x commute because Z is in the center. It's x times Z m lambda. And now, how does Z act on m lambda? This is by chi lambda also. I'll put it by x times chi lambda. That's a scalar times m lambda. And I take the scalar outside. X times m lambda was mu. So chi mu, sorry, chi lambda. So on the one hand, Z times mu is equal to this guy. On the other hand, Z times mu, the same thing, is equal to this guy. And this is true for every element of the center. So what does that tell us? It tells us that these two algebra maps, chi mu and chi lambda, are the same algebra. They are exactly the same map from the center to the scalars. And the first ingredient in both of them was the same also, the projection to the symmetric algebra of H. It's the mu thing lambda applied that don't change it. They still remain the same. So chi lambda equals chi mu on Z if m lambda has a maximum vector. So that is much more difficult, than looking at some nice SL2 calculations here. In the semi-simple case, one has to use the full power of the center, not explicit calculations, which are hard, which are very, it's not possible to do them in general. But here you have, and then now here is where you use the theorem. So of course, page G is semi-simple. See, this happens if and only if there exists a while loop element W such that W lambda and mu are essentially in the same orbit of the while. But essentially means that you have to add this row. Row is the half sum of the positive roots. Let's call this beta. We called it beta, so I'll call it beta. Beta and 5 plus. And another formula for rho, since we remember the fundamental weights that we have defined, is the summation of the fundamental. You remember I had defined these things as the dual basis with the angle bracket. So this is another formula for the same vector in X star. Okay, so this is Harishchandra's theorem. So now we therefore understand which are the only possible vectors that occur, which are the only possible highest weights that occur for maximal vectors in a Varma. They have to come from this twisted, this dot. This is called and did you define it, Ravinder, this action?
Yes, because
Yes.
MSI dot lambda is contained in M lambda I use.
Yes.
I proved it. Yeah.
Yeah, I saw the notes. Like, okay, good. So called the dot action or the twisted action. You said that the W dot lambda equals. This is how we write. That's the same as saying that mu equals W of lambda plus rho minus. You solve for mu, take the rho on the other side. So this is therefore the final answer to this question. So yeah. So the final answer is yes. So the final answer is therefore. Are mu and lambda related? So there are two things. Yes, mu and lambda related as follows. Related by two things. One is that mu is in the W action, the W dot orbit of lambda. There is some value element, little w, belonging to big W, such that mu is little w dot lambda. And the second, this is a pretty obvious thing, is that if mu occurs as a weight space, as a weight vector of Varma module, remember that the entire Varma module is generated by these guys. So therefore, what happens when you apply some lowering operators, let's say f j times m lambda. This has weight how much? Can anybody tell me?
Lambda minus J.
Lambda minus. This is not in SL2 anymore. This is in any
Alpha
sense. Yeah. Lambda minus alpha.
Yep.
Right. So therefore, now when I apply un minus, remember that n minus was generated by the lowering operators. So any word in un minus, so any PPW kind of word, its weight will be a sum of combinations of alpha j's. So basically, therefore, lambda minus mu, or I can say mu minus lambda, belongs to minus, so it's a negative integer combination of the same. Or if you want to get it, mu belongs to lambda minus. I can move the lambda to the other side of the belongs to. So these two are necessary. The moment you have a maximal vector here, it is necessary to have mu belong to both the twisted while orbit and the cone starting from lambda. You start subtracting alpha 1s and alpha 2s. This is lambda and this is minus alpha 1, minus alpha 2, and so on. Mu belongs to mu is one of these. And it is in the twisted while orbit of this. There is some twisted while orbit. So that makes it sort of, it only belongs to very few set of points. It can't belong to very many. It can't belong anywhere outside. So only this here, something. Okay. So there are very few points where you can belong. So this already places severe restrictions on what kind of submodules you can get inside Varma. Okay. So I think now with this, it's probably time to start to define the main object of this series of lectures, the category O. Yeah. Maybe I should do one last thing before I do so. I should remind you of the basic properties that Ravindra had stated about Varma modules. So it's 5, so we call it 6. Just a last reminder, and then we will define the category. So first of all, the definition, a highest rate module. Of highest rate, let's say mu, is a G module M with a vector M of with a maximal vector with a maximal vector M of weight mu such that M itself is generated by. For example, you have the one module. So what are some basic properties? The sets, facts, and just call them facts. If you haven't proved them earlier, then you can ask the tutorial. So one is that e.g. one example is Varma module, but not just that. A module is highest rate if and only if a Varma module certifies. So M is of highest rate. I'll just say M is of highest rate mu if and only if M mu subjects on it. Which is just the same as you take the vector M here, you take the vector mu here, which is the image of 1, and you map mu. And then n minus mu to n minus n. M is semi-simple with respect to which M. Okay, so M is of course equal to un minus times mu. M that comes basically from the subjection, if you will. Or we saw this earlier. Is H semi-simple. Meaning that you can find an eigenbasis. You can find the basis of this vector, vector space module, which is a simultaneous eigenbasis for the entire Cartan algebra. And not only that, and now here is where maybe I should mention, if you take any quotient module of such a module, you still get another highest rate module because quotients of quotients are quotients. So that also that's semi-simple. Okay, there's nothing much to say there. But what you can say is that any submodule is also X. And I should point out, I should actually have said it here already, but maybe I'll say it here, with finite dimensional H weight spaces. So maybe I should give a definition here, which will be very useful later. So given a G module M, and I could take an H module also, but let's just say G module. And the weight mu, define the mu weight space, which again Ravindra must have done already. To be M mu is the M here, which are eigenvectors with mu as the eigenvalue. H okay, define the mu weight space. So then when I say that M is H semi-simple, this is the same as saying I should just say IE. M equals, if you take mu in H star, mu was already decided. Let's take a mu in H star. M mu. It is a direct sum. So and then the same thing is true here. It is a direct sum, and every single eigenspace has finite dimension. that thing will again show up. So this is part of category O. When we define it, we will see this condition show up. Oh, actually, the whole condition. It's semi-simple with finite dimension. Okay, so what else do I want to say? In particular, we can calculate the dimension. In particular, you can calculate the finite dimensional spaces. Here is a very specific, very special module. The biggest highest rate module. Because it subjects onto everything else. So we can ask what is the dimension of m lambda, or maybe I can do this since we are doing this thing. Right. What is this dimension? And this also I think Ravinder did. Basically, remember that. So what is this? M lambda, M mu. The point was to write what M mu is. M mu is un minus applied to M mu. And here I want to understand what is the new. What am I doing here? We said that somewhere. I forget, on the previous board, that we keep applying monomials, maybe like f1, f2, f1, 2, etc. Some monomials, power a, power b, power c. Apply them to mu, and the rate that you get is mu minus a alpha 1 minus b alpha 2 minus c times this negative weight and so on. Root. Right. So this is how you get curves. So you fix some PBW ordering of the n minus, meaning you fix some ordering of the negative roots. Every negative root space is one dimensional, that we have seen earlier. Therefore, un minus can be written in terms of the words in some ordered basis of the corresponding to negative roots. And now we want to say that, well, we want to say this has weight is mu minus a alpha 1 minus b alpha 2. Sorry, mu, this is mu. So mu minus this guy equals, and this should be equal to nu because I get some words. So how many different PBW words would give me the correct weight? That is exactly the dimension of the weight space. And that was called the constant partition function. This is the number of ways to write. Let's see what. Mu, so mu is bigger, mu is smaller. So mu minus mu as a sum of negative roots. And now not just negative simple roots. N minus has all non-simple root spaces, simple root spaces, everything. Therefore, as a sum of negative roots. I'll do an example in a minute. Less than a minute. This is called the constant partition function. KPF, maybe I'll just call it KPF. Is there a notation for it? This is some little p or something. KPF of mu minus. So let's do an example of this. But this is just to tell you that there are only finitely many. Everything here is finite. QoS. I'll keep it. I have in my mind it's KPF. So for many years now. Okay, so for example, let's say G is SL3. So n minus, so let me just take 5 minus the negative roots are minus alpha 1, minus alpha 2, and minus theta, which is minus alpha 1. There are 3 roots. 3 positive, 3 negative. Right? So now for n minus and correspondingly n minus, what is this? It is spanned by, so basis is minus alpha 1 corresponds to let's call it the elementary matrix E21, E32, and E31. Which we are, of course, right, that this is the lowering operator F1, this is the lowering operator F2. I can call this F1 if you want. So words, so therefore, so UN minus is the span, is the C span of what is F1 to the space, F1 to the A, F2 to the B, F1 to the C, which is what I have written somewhere here in the IISc. ABC. This is what UN minus is. And in this order, I'm not going to change F2 power something with F1. I've chosen my convention. My ordering is this, and this, corresponding to that the basis vectors are this, and this. So the words are this power A, this power B, this power C. And now I just want to understand, for example, so what is, for example, let's do an example. So what is the dimension? Take the Varma module of I squared 0, and now all the root spaces, all the weight spaces that belong, it have to be some negative sum of simple, because M0 is 0 minus roots. So this is, let's say, what minus, say, 2 alpha 1 minus 3, maybe minus 2 alpha, minus alpha. So how do we answer this? We have to write down this vector minus 2 alpha 1 minus alpha 2 as a sum of negative roots. The other way to say it is you have to write down 2 plus 2 alpha 1 plus alpha 2 as a sum of positive roots. So either way is fine. Let's just do the positive so that I don't have to keep writing minus sign. So 2 alpha 1 plus alpha 2. Okay, can somebody tell me one way to write it as a sum of positive? Anybody? How do you write this as a sum of positive?
Yeah, alpha 1, then alpha 2.
Right? We take individual roots and they're positive. And another way,
Also, you can clump alpha 1 plus alpha 2 together.
right? Right. Turns out these are the only yes. So therefore the dimension of this thing is 2. Because there are 1 and 2. If I asked for something like M0, maybe I'll how about this? How about M alpha 2 minus 2 alpha 1? I change the highest weight. I keep the weight space the same, but I change the highest. Now again, I have to go from alpha 2 to this vector. So I have to lower from the highest weight vector of weight alpha plus alpha 2 to get to a weight vector of weight this. That means I'm lowering by minus 2 alpha 1 minus 2 alpha 2. So I have to write down 2 alpha 1 plus 2 alpha 2, or you can take minus signs. Now how many ways are there? So again, first of all, I can do this. I can do alpha 1 plus alpha 1 plus alpha 2 plus alpha. Okay, I can do that. I can also say, now what else can I say?
Theta plus theta is also there.
Right, so I can have theta plus alpha 2. This is like this one, and now I can write down theta plus theta, or 2. So the idea is that basically, of course, addition is commutative. So you write them down in whatever order you fix an order of writing. Here I should call it theta. So I'll write down first the theta coefficient, then alpha 1 coefficient, then alpha 2 coefficient. And I want all tuples of distinct, all possible distinct tuples of coefficients, such that the sum is exactly equal to the difference between this highest weight and this weight. And so therefore here the dimension is 3. And so this is just a very combinatorial and nice game to play with, roots, the set of negative roots you have. Write something as a sum of negative roots, or write it negative as a sum of positive roots. And find out all the distinct ways you can use. That number is a finite integer number. That's the dimension of the expression. Okay. Until then, what time is up?
Yeah, Apoorva, yeah. Do you want to take a 10 minutes break? Yeah.
No. I think we will stop here, and Teja will do the tutorial at 12:45.
Yeah,
Then
it's in 10 minutes. Yeah, that's
Yeah.
fine.
So yeah, we take a 12-minute break or something, and
Okay,
then I
fine.
will do next time. Yeah, Teja will start with. So next time we will finally define category. Okay, we'll stop here. So should I just shut off the video? I'll just leave the video on. Is it okay? People
Okay,
can
no
ask.
problem.
and Tejas here. Wherever you want. You want to do on your tablet? Okay. Yeah, if you have questions, please ask. I'm still here. I can give you hotspot. Oh, you want to use any hotspot? But EduRoam was sent.